Let us now discuss how to provide current limiting for the series regulator circuit. Now consider the series regulator circuit and let us introduce some components here such that we limit the current under overloading or short circuit conditions. Now let us create some space here to introduce some components here, and let me introduce a resistance in this fashion, and across the resistance let me connect the base emitter of a transistor, and the collector of the transistor is connected to this point. Let us call this transistor Q3, this is RS, and I0 flows here. You can say I0 is the current flowing here is approximately equal to I0 because the current flowing through this feedback tap point is very negligible. So let us say this I0 value which is flowing here is dropping across this, and you have I0 into RS drop. So this I0 into RS drop is the one that will start cutting in this transistor Q3. So once the I0 into RS drop reaches 0.7, so that is where you can design the value of RS for a given I0 rated value. Once it crosses 0.7 at say the I0 rated value flowing through this, the transistor will be almost reaching the saturation stage, and it will be drawing a large amount of current, reducing the base drive here and thereby making this more towards the off region, and it will be withstanding more and more voltage. Imagine a condition where you short circuited the output. When short circuit the output, the voltage here is 0, a large current is expected to flow, but IRS drop will drive this into saturation and take away all the current, IRB current into this, and Q1 will be in the off state and withstand all of VI. So this is the constant current limiting. So if we take VR, this is VRS. So VBE3 across this is nothing but I0 into RS, and RS can be selected by VBE3 divided by I0 rated, whatever is the rated value for which you would like to provide the limit. So around 0.6 volts for VBE divided by I0 rated will be the value that you select for RS. So if you plot the I versus V, I0 versus V0, so at V0, whatever be the load, V0 is going to be constant till it reaches a rated I0 rated current value. Beyond I0 rated current value, this would be draining out the drive for Q1, and Q1 will support the entire voltage. So even if you short circuit it, this is the short circuit means 0 V0 point, that is here. So it will limit the current to I0 rated. So this is a constant current limiting type of a circuit. Very nice circuit, which can be used in most of the series regulator type of configurations. Let us look at another interesting current limiting technique called the foldback current limiting. We had seen this constant current limiting by putting these set of components, one BJT, Q3 and RS. Now let me modify this slightly and you will get this foldback current limiting. Now let me explain this. Let me remove this portion, make a bit more space, and I will put the resistance RS here. And from this point I will tap a voltage divider to ground, and to the center point of that I will connect to the base of the BJT Q3. So the collector I connect it in the same way, and the emitter also I connect in the same way to this point, output point. So by making this small modification, you will find an interesting way of current limit. We'll call this Q3, we'll call this RA, RB, and this is RS. The potential here is this drop I0 into RS plus V0. Okay, so I0 into RS plus V0 will be the potential of this point with respect to ground. Potential of this point with respect to ground is V0 itself. Okay. Now let us look at the potential of base emitter of Q3. So we'll call that one as VBE. VBE is equal to this potential, which is whatever this potential I naught RS plus V naught with voltage divider action of RA RB. So which will be I naught into RS plus V naught multiplied by this ratio RB by RA plus RB will be the potential at this point minus the potential of this point, which is V naught. So we will get that as the voltage across VBE3. Now I will define the symbol alpha for this RB by RA plus RB so that equation becomes simpler to write. And we know that alpha is less than 1, varies between 0 and 1. Now VBE3 can now be written as alpha I naught RS plus V naught minus V naught. Okay. Now you can simplify it a bit further. Alpha I naught RS, I will take it, and this V naught and V naught, I'll take it common and write it as 1 minus alpha V naught. Note the sign change here accordingly to take care of this. So now on short circuiting, let us say I short circuit this. So V naught becomes 0. On short circuiting, V naught becomes 0 and I naught, we will call it as ISC, short circuit current. Okay. Here again, assume that the current flowing through R1, R2 is negligible and therefore this value is I naught itself, whatever is flowing through the load. So under short circuit condition, look at this equation, V naught is 0, so this term goes off and you have only this term. So therefore ISC, this I replace by ISC, which is equal to VBE3 divided by alpha RS. So this is a design equation for choice of RS and appropriate choice of the design parameter alpha. You can also design what should be the short circuit current. Now this importance will become clear as we go to the next steps. Now consider this equation. So I can now write I naught equals VBE3 divided by alpha RS plus I am bringing this term onto this side 1 minus alpha V naught by alpha RS. Now this equation, you have VBE3 by alpha RS. VBE3 by alpha RS, we have defined it as ISC, short circuit current. So I will write I naught as ISC, short circuit current, plus 1 minus alpha V naught by alpha RS. So this equation, interesting equation, if you plot V and I naught and V naught, find this interesting. So this region V naught, this region, as whatever be the load change here, I naught change, V naught is constant till it reaches I naught rated. So this is I naught rated. This circuit will operate in the normal mode, regulation mode, for all the loads which appear here till I naught rated. Now let us say I apply a short across the output, R naught is made 0. So the moment R naught is made 0, V naught becomes 0, this term vanishes. So I naught reduces to ISC. Actually I naught, when it was operating in the normal operating mode, a value of I naught here is ISC plus something. And now V naught is made 0 under short circuit condition. You will see that this would be the operating point, ISC, because V naught is now 0. And this is the fold back. So when it was operating at I naught rated and something happens, a short circuit happens, you will see that the current that flows will be lesser than the rated, thereby protecting the devices. And this is called fold back current limiting or current protection. An interesting circuit which can be used by you for any series regulator.